Joan Sola, the running vacuum model, a possible consistent overarching view of the cosmological evolution. Please, Joan.
Yes, thank you. I am trying to share my screen, and it says that host disabled participant screen sharing. So if you allow me to share it.
Okay.
Very strange.
I mean, they have to find you here. Okay, Joan, here. There, fine. There you are.
Okay, good. Thank you very much. So I hope you can see now my presentation, the first page. Is that right?
Yes, indeed.
Right.
Okay, very good. So first of all, thank you very much for the invitation to this online conference, okay? So it would be much better to be here with all of you, but we have to content ourselves with this. So the title of my talk is the Running Vacuum Model, a possible overarching view of cosmological evolution. So the basic content is about vacuum energy, the cosmological constant problem, and dynamical dark energy and running vacuum, and the implications on some issues like, for example, the Brownian gravity and the so-called lambda CDM tensions or troubles. Okay, so of course this talk is about the universe, right? So what we may call the Todo or das Ganze, according to Heisenberg. Okay, but of course this Todo is what we call cosmology nowadays, and this cosmology and this Todo is made of the Parte. And partes, for example, are atoms, like these atoms from proteins, but in a more fundamental way from particles. So these particles, of course, will be involved in the evolution of the Todo through what I call this running vacuum model idea. It seems, according to the great master, that we are also part of this whole, okay? Let us see if we can say something useful about it. Again, following the great master and the great equations, Einstein equations, which were introduced long ago, and 2 years later, Einstein, as you know, introduced the term, which was called the cosmological term. In any textbook, it is shown that under simple assumptions, this term must be constant, but if you abandon these assumptions, then it may be an evolving quantity. In any case, once you have lambda, you may define through this Newton's coupling another quantity which is called the vacuum energy density, because it is related to the density of something which is not matter, right? And in general, you may call it dark energy. So here you have the paper where Einstein introduced this term long ago, 1917. And 14 years later, in another paper, which is called about the problems of cosmology, the problem here was that he wanted to reject actually the introduction of lambda, which had been introduced 14 years before in this other paper, okay? Actually, 2 years later, Einstein wrote this famous paper with de Sitter, in which he presented the CDM model, not the lambda CDM model, just the CDM model. It was not called that way at that time, but it is so. And in fact, in this sentence that you can find here, it seems that lambda is no longer necessary in his cosmological Weltanschauung, okay? 2 years later, Lemaitre resuscitated this term, okay? And it has a longer story. I will say something more about it. But what is important is that after 104 years, it is still with us, and we still don't understand what is its ultimate meaning. But it is also true that already 50 years later, after Einstein introduced his cosmological term, Seldovich, 1967, proposed this connection between lambda and quantum field theory through the vacuum energy density. He made these famous ansatz in which by just dimensional analysis, rho lambda is proportional to the quartic power of any mass looping around this loop, okay? He used the proton mass, doesn't matter. Any particle gives a very large value, except a very light neutrino, of course. But even in this case, which he used, the proton mass, it gives, of course, a value which, when compared to the critical density, which is essentially the value of the cosmological vacuum energy density, it is, as you see, 47 orders of magnitude away. Then he did this second thought attempt by dimensional analysis by using G together with the mass of the proton. He got a much smaller number, but still unacceptable. If we come to more modern ideas, the value of the vacuum energy density is the sum of two quantities, which is what we may call the vacuum term present in the Einstein-Hilbert action or in the corresponding Einstein equations. And then there is also an additional contribution, which we call it lambda induced. And this lambda induced is made of also of two terms. One is connected with spontaneous symmetry breaking contributions, for example, the Higgs mechanism, and the other, which is purely quantum. It is this 0-point energy, okay? What is 0-point energy? Well, it is something like this. The vacuum is full of fluctuations, okay, with no external tails, and we have to sum over all the modes, so the vacuum is full. So there is, it is not the classical Aristotelian vacuum with full of emptiness. No, it is full of quantum fluctuations. Apart from that, as I said, there is the contribution from the Higgs potential. Of course, I will not review this, which is well known, but just to say that it is very important. In fact, it is essential in order to explain what we have seen about the Higgs, of course, and also to explain about the origin of, for example, the W and Z boson masses. So the vacuum is a complicated object, which is a combination of quantum bubbles and spontaneous symmetry breaking. And it seems that for some mysterious reason, they conspire in such a way that, or at least this is what is claimed, it has been claimed for a long time, that they conspire in such a way to give the value, the tiny value that we have measured. But of course, this conspiration is very strange, because if we take any whatever typical contribution, for example, the electroweak standard model, which is well known, and we compare with the value of the cosmological vacuum energy density that you obtain from the critical density, you get a number which is 56 orders of magnitude away. So that's why people try to go beyond lambda through this more general concept of dynamical dark energy, right? There are various forms of this dark energy. So in a very schematic way, we take the densities and the history of the universe. We have radiation, then we have matter. Then people assume that there is something else called some scalar field, which called quintessence, which at some point near our time, it surfaces, okay, and it decays. But there is also a possibility that there is something similar which surfaces at around the same time, but rather than decaying is increasing, which will be, if it is the case, it will be a total catastrophe, because it will cause a big rip. Okay, so these ideas are well known, they are well developed since long ago, but I want to come back to vacuum energy. So take, for example, 0-point energy in quantum field theory. Take, for example, this expansion in loops of the 0-point energy. Take just the one loop contribution, which is this sum over the modes that I have shown before. Of course, you convert this into an integral, you normalize this theory in a typical way, let us call it this way. And what you find is that the normalized value is proportional, or at least it gets a contribution which is proportional to the quartic power of the mass of any particle. And of course, this causes a lot of headaches. The reason for this quartic contribution comes because you have these blobs, as I have shown before, But of course, in the context of gravitation, even in the case where gravitation is an external field, namely quantum field theory in curved space-time, then you can also consider diagrams in which you have vertices with external tails of the gravitational field, which are no longer quartically divergent, they are quadratically divergent, or even logarithmically divergent if you introduce the two vertices, okay? So for example, if you consider these diagrams here, which normalize the value of G, and you take, for example, the running scale mu that you would use in whatever calculation that you do, and then you make an association with some quantity. For example, suppose that you make the association that mu is basically given by the value of the Hubble parameter, which has dimension of energy. Then what you find is that the gravitational coupling gets this running law, a logarithmic law, in which nu would plays the role of the beta function. Okay, when you combine this expression with the other equations of cosmology, the Freeman and the Bianchi identity in this case, in which reflects the interaction between the change of G and the change of rho lambda, what you get is an exact solution, which is this one here, which says that rho lambda is essentially constant, which is what we want. But apart from that, there is another term, which is this C2, which is small. It's a tiny number because it is proportional to the beta function. And therefore, it suggests that rho lambda is constant plus some mild evolution. Now, of course, if you go further and you extend this idea in a systematic way, something that we proposed long ago with some colleague, 20 years ago, actually, amazingly enough. And then we, of course, made some new developments with time. We have, you can consider that that the cosmological term, or even the vacuum energy density, okay, it is made of an expansion in powers of h, okay? And you can even test whether this is good or not from the phenomenological point of view. And in fact, this is what we find in a series of papers with my students and other people, and we find that it gives a better fit to the lambda than the lambda CDM, and it alleviates the famous H0 and sigma 8 tensions. For low energy physics, of course, from this series, you only need the first term, okay, which you can, of course, normalize in this way, such that when H is equal to H0, you get the value at present. But if you want to get, if you want to get a view which is motivated in the context of string theory, which is something that we have developed very recently, please attend Nick's talk on Wednesday, or just have a look at our review, which we issued last month. So as I said, the idea behind this story is some renormalization group equation concerning the evolution of rho lambda, which when solved give this expression with all the powers of the Hubble parameter, derivatives, and so on and so forth. You can, for example, take this canonical version in which you have the h squared term, as I said before, and you can also consider the next term, the next even term, even because we want to have compatibility with general covariance. And from this term, you can trigger inflation. This is interesting because this is the kind of inflation that you get from this formulation of dynamical vacuum energy is distinct. Is quite different from Starobinsky inflation, because here you can have inflation with h equal constant, which is not the case with the Starobinsky. So these terms are important, okay? But it is also important to have also some more fundamental substantiation of this structure, not just some general motivation from renormalization group and so on and so forth. This is actually that we have done very recently with a student of mine, Christian Moreno, in which we took this quantum field theory on a Freeman-Lemaitre-Robinson-Walker background. We took a scalar field non-minimally coupled to curvature, And then we computed the energy momentum tensor. This is very easy, just the classical one, of course. And then we add the quantum fluctuations, and we consider just the vacuum part of this energy momentum tensor, which will be given by the cosmological term plus the vacuum fluctuations. Of course, the vacuum fluctuations, you get it from the expansion in Fourier modes, for example. Then you have this mode equation in which this effective frequency gets a non-trivial correction from gravity through this R term. Psi is, of course, the non-minimal coupling. Of course, if the non-minimal coupling is 1/6, we have conformal coupling, and then you get 0. Now you have to solve this, which cannot be done exactly. So you made this attempt, this phase integral, in which you replace this variable in terms of WK. This WK defines a non-linear differential equation, which can be solved through WKB approximation. And basically, you end up with an adiabatic expansion of the solution, which takes this form here. And this form, as you see, it only contains terms of adiabatic order 0 to 4, even adiabatic order. This is, of course, welcome, because this provides an expansion only in even powers of H. So these powers that they have shown before, you have to cross them because they cannot be there. They would be incompatible with the general covariance. So indeed, you get an expansion in even powers of H, the Hubble parameter, okay? And you compute the various contributions. These contributions are given in terms of the scale factor. This tau is a conformal time. Here we use some arbitrary mass scale. A particular case would be when this scale is the particle mass, then you would be in an on-shell expansion, but we do it off-shell. And we also introduce the difference between the on-shell value and the value that you are considering. Okay, so now you just put all this in the expression of the expectation value of the energy momentum tensor of the fluctuating field. You put the solution here, and you get a complicated formula. What is important to remark in this formula is that all the red pieces are divergent. They are divergent. So this is, of course, an unrenormalized 0-point energy. So, of course, you have to renormalize. We renormalize by subtracting the on-shell value at this scale M, an arbitrary scale. So you do this, and then you can compute what could be the final renormalized value, adiabatically renormalized value of the vacuum energy, which is made out of two pieces, the normalized value of rho lambda and the normalized value of the energy momentum tensor at that scale. And when you compare two different scales, M and M0, which would be like comparing what is the value of the vacuum energy at two different instants in the evolution of the cosmos, then you find that the two values are connected precisely in the way that we had foreseen many years ago, which is just a term proportional to h squared, and then other higher order terms, which are of order h to the fourth, okay? These terms, however, do not involve h to the fourth. They involve derivatives of h, but they are homogeneous to h to the fourth. In any case, at low energies, the dominant term is the h squared term. So you get just the constant contribution plus an h squared correction. And the relation between the two values at different scales do not involve the quartic contributions, which you remember that they were a headache because this causes fine tuning, but you don't get it here by doing this adiabatic renormalization. You can even repeat the same story by subtracting the Minkowskian contribution from the Freeman-Remeter-Robinson-Walker result, and you get exactly the same result. I mean, if you want to have details, please have a look to our paper, which is published in Neurophysics Journal C at the preprint number that I have given. So basically, I cannot go into much details here. The value of the vacuum energy, say at the present, is given by the value, not at present, at some instant of the cosmic evolution, when the Hubble parameter takes some value, is compared to the present one in this way, right? And then you see that this parameter here, which is the one which controls the evolution of the vacuum energy, you see that it's computed in a precise way, and it is naturally small. Why it is small? Because it is a ratio between a typical high scale where you define the couplings, say a GATT scale, compared to the Planck mass. So of course the GATT scale is below the Planck mass, something like 3 orders of magnitude. So you expect that this parameter should be small. So the departure of the vacuum energy from the value that we measure at present should also be small, but maybe not that small, because after all, there is a coefficient here, and you have to sum over the multiplicity of all the particles. So at the end, it could quite be that the parameter is, say, of order 10 to minus 3, and give some correction. Now, this concerns the evolution of the vacuum energy near our time. But what about the early universe? The early universe, as I said in a previous, well, I will not go to that point, but remember that there was a quartic contribution of the Hubble parameter. This was very important in order to trigger inflation. And this kind of thing, recently with some collaborators, including Nick Mavromatos, which is here, and also Spiros Vasilakos, what we did, you can see this detailed review that we issued last month. We have shown that in the context of effective string theory at low energies, when you consider the bosonic part of the action, there is some terms, for example, this Chern-Simons density, in which you have this coupling with this Carl Ramon axion. And when you compute this, and of course, Nick will talk about these details, you find contributions of order h to the fourth. So this is very nice to see that this h to the fourth contribution can be also substantiated in the context of string theory, which after all, it is what you expect in the early universe. Whereas at the present universe, of course, you don't have any effect at all. So if you have this theory with h squared and h to the fourth, this is basically accounted from quantum field theoretical calculations, and this part from string theory calculations, then you can solve the corresponding equations for the Hubble parameter, the densities, using the inflationary values, okay? And then you get this curve in which you have an initial vacuum density, okay, which is decaying. You have zero matter in the beginning, but matter, meaning radiation, is increasing and then again decreasing. And if you consider the whole history of the universe, this is the part that I was showing before, then you get, of course, the various contributions from vacuum, matter, and radiation, in which the vacuum itself is evolving and not just the matter and radiation, okay?
Okay.
So, yeah, so basically, let me show that when you consider all the data that we have, the modern data that we have at present, in a series of papers, we have shown that this parameter nu that I have mentioned, which we have computed theoretically with some unknowns, but in any case computed theoretically, you can fit it to the data, and as you can see, the fit gives a non-vanishing value, which if you look closely, it is of order of 10 to the minus 3, okay? So it is also remarkable, as we have shown in these recent papers, that this running vacuum model idea is mimicked also by other frameworks, not just general relativity with these running vacuum terms, but also in the case of Brans-Dicke theories with the cosmological constant. It turns out that it also mimics this term. Of
Joan,
course,
sorry,
yes?
we are out of time.
Yes. Okay. So just to tell you that when you compare with these sigma tensions, sigma 8 and 80 tensions, you also get a better agreement, okay, as compared to the standard model. And so finally, I'm the end, okay. So the last thing I want to say is that this idea of dynamical dark energy and running vacuum models may provide perhaps a connection between the large scale structure of the universe and the quantum phenomena of the microcosmos, the part of the La Parte, right? Because La Parte, the particles, are the ones which are running our equations in order to explain the Todo, the universe, okay? So perhaps they can also give new vistas on how to solve the famous CC problem. Many thanks for your attention.